In lab number 2, we'll take a look at our first dynamic routing protocol, specifically RIP, the Routing Information Protocol. We begin by introducing RIP, and we're going to see that we have a couple of different flavors that we're going to be dealing with in this lab. RIP version 1 and RIP version 2 will contrast those. We'll see the syntax for setting up RIP. Then we go out to our live topology, configure RIP version 1 first. Then we'll follow that up with RIP version 2, and we'll make those two different versions peacefully coexist in the same network. Oh, and RIP version 2 supports something that RIP version 1 does not. It supports authentication. So we're going to set up authentication for RIP version 2, and then we'll verify that configuration.
Let's begin by taking a look at what the Routing Information Protocol, or RIP, is all about. First up, let's think about how RIP can influence the routing decisions of our router as its metric, as its way of deciding which path is the best path to a remote network. It uses the very unsophisticated hop count metric. Specifically, if we take a look at our topology, if we were on router R2 and we wanted to see what the hop count was to network 172.16.1.0 as an example, we would take a look at how many hops or how many routers we had to cross in order to get to that network. In this case, we would have to pass through router R1. So that would be one hop away from the perspective of R2. Now, while hop count might not necessarily seem like a bad thing, think about this. What if one path to our destination network was a single hop? It had a metric of 1 according to RIP, but that one hop was over a 56 kilobit per second circuit. Another path to that same network might have been over a 2-hop path. So RIP is going to prefer to use the 1-hop path, even though that 2-hop path might have been comprised of T1 links. So we could look at the topology and know that it would be better to go over that 2-hop path, but RIP is only considering hop count. And that's one of the reasons that RIP isn't considered to be a very sophisticated protocol. Something else to be aware of when it comes to RIP: the maximum number of hops through which we can pass before a network is considered unreachable is 15. We have a maximum hop count of 15 hops. Once the hop count goes up to 16, RIP considers that destination network unreachable. But a characteristic of RIP that we like very much is its ability to load balance across equal cost paths. So in other words, if we had 4 different paths to get from one router to a destination network, if they all had the same metric, they all had the same hop count, RIP would load balance across those 4 different paths. That's the default setting. That could be increased, by the way, up to a maximum of 6 paths over which RIP could load balance. And we mentioned back in Lab 1 that RIP was considered to be a distance vector protocol. Remember one of the characteristics we spoke of when it came to distance vector routing protocols? We said that with distance vector routing protocols, we were periodically going to advertise our entire routing table out to our neighbors. Well, by default, RIP is going to advertise its entire routing table out to its neighbors. But there's an exception to that. RIP will not advertise a network out of the same interface over which RIP learned that network. That's something called split horizon to help prevent routing loops. So to illustrate on screen, if R2 were running RIP and R1 were running RIP, and R2 received an advertisement about network 172.16.1.0, it would have received that advertisement via fast Ethernet 0/0 on R2. R2 would therefore not advertise that same network back out of fast Ethernet 0/0. And when we speak of RIP, realize that we have a couple of primary versions of RIP, and this is specific to IP version 4. There is another version of RIP, RIP-NG, that can be used for IP version 6, but our focus is on IP version 4. You see that RIP version 2 has quite a few advantages over RIP version 1 by taking a look at this table on screen. First up, RIP version 1 is a classful routing protocol, while RIP version 2 is a classless routing protocol. In other words, when we advertise a network using RIP version 1, that network can only be advertised using that network's classful subnet mask. For example, if we had a Class A network that we were advertising, like the 10. network, even though we might have that 10. network subnetted into many, many other subnets, we would only be able to advertise that 10 dot network, including all of its subnets, as a single 10.0.0.0 route advertisement with an 8-bit subnet mask, because it was a Class A network. Similarly for Class B, those networks would be advertised with a 16-bit subnet mask, and a Class C network, that network would be advertised with a 24-bit subnet mask. We do not have that limitation with RIP version 2. It's a classless routing protocol, so it can carry subnet information as part of its routing advertisements. And as a result, RIP version 1 does not offer variable length subnet mask support or VLSM support, while RIP version 2 does offer VLSM support, where we can have different subnet masks applied to different subnets of the same major classful network. Another big advantage that RIP version 2 offers is its support for authentication, while RIP version 1 does not offer authentication support. And when we're speaking of authentication, we're talking about one router authenticating another router. That way we don't have an attacker maybe introducing a rogue router into the mix and trying to propagate out false routing advertisements into the network. We can help prevent that type of thing from happening using the authentication of RIP version 2. And there's a couple of ways of doing this authentication. It could be done using plain text, or to be a bit more secure, we could use MD5, Message Digest 5 authentication. And in this lab, we're going to show you how to set up authentication for RIP version 2. And another distinguishing characteristic between RIP v1 and RIP v2, when RIP version 1 sends out its advertisement, it sends it out via a broadcast. Contrast that with RIP version 2, which sends out an advertisement via a multicast. Now that we've reviewed some of the basics of RIP, let's see how we're going to deploy RIP in our lab topology. You might recall that this is the same core topology we had back in Lab 1. I did make one slight change since Lab 1. I added loopback interfaces to all of the routers. Now, what is a loopback interface? A loopback interface is a virtual interface on a router that never goes down unless we shut it down. And a loopback interface can be great in a lab environment when we want to check connectivity to all of our different routers. So notice I've numbered the loopback interfaces on these routers with very easy to remember IP addresses. Router R1, for example, has a loopback IP address of 1.1.1.1 with a 32-bit subnet mask. In other words, that loopback interface is for a subnet that only contains that one IP address. Router R2 has a loopback IP address of 2.2.2.2. So after we get RIP set up here in a few moments, we should be able to go to any router and ping the loopback interface of any other router. That's a great way of checking for connectivity. And we mentioned that we had a couple of different versions of RIP. Well, the first thing we want to do, we want to set up RIP version 1 on routers R1, R2, BB1, and BB2. And we want to make sure that we can reach one another. And we want to see how route information has been advertised into these networks. And if you look very closely at the IP addressing scheme on screen, you might see that we could have a concern. Specifically, remember RIP version 1's limitation of being a classful routing protocol? We said that if we had a Class A network, we could only advertise that network via RIP version 1 using an 8-bit subnet mask. But look on screen, off of router R2, we have a 10.1.2.0 network with a 24-bit subnet mask. And between routers BB1 and BB2 over that frame relay permanent virtual circuit, we also have a 10 dot network address space, do we not? 10.1.1.0. That could cause an issue for us. We'll have to see what happens when we turn on RIP version 1 for these routers. And then, after we turn on RIP version 1, we want to see how we might support a mixed environment. What we're going to do is allow RIP version 1 to run on router R2 and the fast Ethernet 0/0 interface of router R1. But let's pretend that R1 is connecting into a corporate backbone or a service provider backbone that requires that it speak RIP version 2 and also do authentication. So what we're going to do, we're going to allow R1 to speak RIP version 1 out of its fast Ethernet 0/0 interface, while simultaneously speaking RIP version 2 out of its two sub-interfaces built on serial 0/0. And in addition to running RIP version 2, we said that we also wanted to do authentication. Let's say that the backbone requirement for connecting to any other router is for that router to authenticate with the backbone routers. And notice the backbone routers are authenticating between themselves as well. Let's now consider the syntax that we're going to be using in order to set this up. First of all, regardless of whether we're doing RIP version 1 or RIP version 2, we enter router configuration mode with the router RIP command. That starts the RIP routing process. Then we can give a series of network commands. Network followed by the IP address of the network. And even though we might specify the IP address of a subnet within a major classful network, as we're going to see when we go back and look at the running configuration, that subnet will have been converted into the major classful network. And we're going to give a series of these network commands to advertise on each of these routers the networks that these routers are directly attached to, including the network represented by the loopback interface on those routers. We are then going to turn our attention to RIP version 2. We're going to start running RIP version 2 on routers R1, BB1, and BB2. And a default characteristic of RIP version 1 and RIP version 2 is that they automatically summarize routes. We have to summarize routes with RIP version 1. That's a limitation of RIP version 1. But we can disable the automatic summarization with RIP version 2 to give us more accurate subnet entries in our routing table. That is what we will want to do. A challenge that we have, though, is that we said R2 is going to be a RIP version 1 router, and router R1 needs to speak to the backbone using RIP version 2, but it needs to speak to router R2 using RIP version 1. How do we do that? We can go into interface configuration mode for the interface pointing over to router R2, and we can give the command iprip send version 1. That's going to tell router R1 when it sends RIP advertisements out of this interface, send them in the RIP version 1 format. And then we follow that up with the iprip receive version 1 command to say when we receive RIP information coming into this interface, it is going to be in the format of RIP version 1. At that point, router R1 is simultaneously going to be speaking both RIP version 1 and RIP version 2 out of different interfaces. We then want to add authentication so that these routers can validate that their neighbor on the other end of a link is who they claim to be. They are someone who is authorized to send and receive RIP advertisements. What we do is we go into interface configuration mode for the interface, or in this case the sub-interface, that's going to be pointing out to that neighbor, and we say iprip authentication mode, and we can select either text for plain text, or we can select MD5, Message Digest 5, to send the hash value of our key string that we're going to define, as opposed to sending that key string in text, which might be gleaned from the network by an attacker sniffing the wire. And in this lab, we are going to be using the MD5 mode of iprip authentication. Once we've said how we want to do authentication, we now need to create this string that's going to be used for authentication. That string is a key string, and we can have more than one key on a key chain. And this key can have a particular key string associated with it. Specifically, we're going to create a key chain by saying key chain and we give a name. That takes us into key chain configuration mode, where we define one or more keys. We say key and we give a number for that key, which takes us into keychain key configuration mode. It's here where we specify the actual string of characters that's going to be used for the authentication process. We say key-string and give that string of characters. And we can have more than one key on a keychain. What some people do, they make different keys valid during different times of the day. There's a way of doing that as well. We're going to keep it fairly simple, though. On router R1, we're going to create a single keychain with a single key, and the key string of that key is going to be used for our authentication out to the backbone routers. But the backbone routers, they're each going to have a couple of keychains. They're going to have a keychain that's going